Okay, so before we move forward, I can slightly talk more about this Euler's equation. So actually, the Euler's equation is cosine theta plus I sine theta or J sine theta. Sometimes I used to write J instead of I, and actually I equals to J equals to square root of -1. So if you use, I suppose you have learned the Taylor series, or Maclaurin series. So you know that exponential to x is actually 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial to the infinity. Or you can simply write it as x to the k power, k factorial, k equals to 0 to infinity, something like this. And you also have a cosine x is 1 minus x squared over 2 factorial plus x to the 4th power over 4 factorial minus x to the 6th power over 6 factorial plus dot 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 to the infinity. And sine x is nothing but x minus x cubed over 3 factorial plus x to the 5th power to the 5th power over 5 factorial minus x to the 7th power over 7 factorial plus dot 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 to the infinity. So if you just so this is not only converge for the real number but also for the complex number. If you have chance to learn the complex analysis, you the course may consider about the convergency for the complex function, but for a simple explanation, you can just simply exchange x to I theta into this one, and this one. And then you finally will find that this is what we call the Euler's equation. Euler's equation. So this will occur frequently. So let's move on. So after talk about the single R, single L, single C circuit, we talk about the series RLC circuit, considering the phasor. Yeah. So in this case, the AC source is series with the series RLC, like this. So actually the E is still the same expression, EM times cosine omega dt, and the current is given by I times capital I, which is the amplitude of the current, times the psi function minus phi. Okay, so next, the amplitude, actually you can write it as I cosine function, but the phi may be different, but still a constant, because sine and cosine is just a phase shift. It's just a phase shift. So it doesn't really matter you write I cosine this one, or I sine this one, or I cosine this one. The only difference is the phi is a little bit different with a 90-degree phase shift actually. But in this case, the amplitude of the current phasor is given by EM, which is the phasor of the voltage, the voltage, divided by this one. This one is, well, this is correct, but so far you may be confused how does it come from. And I will say that the impedance of this part of the RLC, the impedance of this part, we call it total impedance for the RLC is RL plus ZR plus ZL plus ZC. So it will be R, which is ZR, J omega L is ZL, 1 over J omega DC is ZZ. So 1 over J is minus J, so it becomes minus J over omega DC. So we only need to add the phasor together to become the series impedance. So we can use the series resistor formula or parallel resistance formula so that we can calculate the series impedance or parallel capacitance. And also the phi will be this one over R, which is actually the imaginary part over the real part. Imaginary part over the real part. And then will be the tangent of the phase. This is yeah. And actually omega D is 1 over square root of LC. 1 over square root of LC. Which means that the current phasor I is maximum. We want to maximize this function. And we know that this is a fixed value. So if we want to maximize I, we need to minimize this term. And R is a fixed value. And this is square, If we want to minimize the numerator, which means that we want to minimize this term, and the smallest possible value for a square number is 0, which means that if this term is 0, then we will have a maximize I. And actually, if this equals to 0, which means that omega D L equals to 1 over one over omega D C. So omega D square equals to 1 over LC. So we have this one. So in this case, ZL plus Z is equal to 0 and phi equals to 0. Then we will have the maximum current. So actually, we can also use the potential method to derive all of this stuff. So similarly, we have EM cosine omega dt equals to VR plus VL plus VC. So actually VR is Ri and L is L di dt, L di dt, and VC is VC, VC is VC, and we know that I would be C dVC dt, C dVC dt. So we have this one here. So we take the derivative of this term so that we have minus omega d Em psi omega dt equals to R di dt plus L second derivative of I plus dVC dt, dVC dt, dVC dt. So in this case, we multiply C on both sides, multiply C on both sides, C, C, C. So that this one will be I, And finally, this is the second order term, and we want to normalize it. So we dy LC, dy LC, dy LC, dy LC. So that finally we will get this one is second derivative of I plus this term R over L di dt, and then this one 1 over LC I equals, this is actually minus omega d Em over L psi psi omega d t, something like this. So we know that on the left hand side, it is actually the same as the one without this source, but on the right hand side it is related to this source, but it's not the same. It has a phase difference, and also the amplitude is different, so that we need to use the KVL to really find the coefficient for the psi function. So if we want to solve this, one, actually if we have the initial condition, then we still need to find the homogeneous solution and then find the particular solution, and then we plug in all the initial value to find the undetermined coefficient in the homogeneous solution. But actually, here what we usually concern is the steady state response, which means that the homogeneous solution will usually tend to 0 as t is very large or tends to infinity. As long as the as long as the system is stable. As long as the system is stable. Because usually when we have a simple RLC circuit, the coefficient is usually positive, which means that the characteristic A and B in this characteristic equation, A and B is positive, A and B are positive, so that the for the roots it will be something like this: alpha plus j beta, and alpha is usually negative. Also, alpha is negative means it refers to the term exponential to alpha t, and if alpha is smaller than 0, it will be something like this. If for alpha smaller than 0, and if alpha is larger than 0, it will grow exponentially. Then this is usually we call it an unstable system. But for simplicity, if we assume that for the steady state, which means that the homogeneous solution will tend to 0, so that we don't care about that, and we use a simpler method to only care about the force response, which is related to this term only to relate to this term. So in this case, we can only substitute the particular solution to be d cosine omega dt plus e sine omega dt, and then we substitute this one into this one, and then we solve for d and e, Then finally we can come up with the solution similar to this, actually the same as this one and this one. And you can check out my note. I have some kinds of derivation. We can solve for d. D would be Em times R over R squared plus omega d L minus 1 over omega d C squared, and E would be Em minus omega d L minus omega d C over actually the same stuff, R squared plus omega d L minus 1 over omega d C squared, something like this. And then finally you use the trigonometry formula. You can know that I will be something like this, and phi is something like this. So we know that so this one is actually so in the denominator here is actually the absolute value of C, and for a complex number, if small z is if small z is equals to alpha plus j beta, the absolute value of z is nothing but alpha square plus beta square, take the square root. Beta square, take the square root. So here we have the r square, which is the square of the real part and the square of the imaginary part. Add them together and take the square root. So it's something like this. It will be something like this. And I think we also need to add the absolute value here, because generally we'll consider about I is also a complex number. I is also a complex number, and which is related to that phase, So I will be the absolute value of I exponential to j phi, j minus phi, something like this. So this is the math in between the phasor. If you don't care about the math, then you can just try to remember all this, or remember all this formula. But it will be quite painful to just to look at them. Well, so let's see an example to have a better feeling about all this complicated stuff. So in this case, we have RLC in series with the AC source. So we have R, C, L, FD, and EM. So what is the phasor of the current? Current phasor. So here we have Z equals to R plus J omega L minus 1 over omega C. So R is 200 and J is omega is 120 pi, and L is 230 times 10 to minus 3 minus 1 over 120 pi. C is 15 times 10 to minus 6 farad. Okay, so Z is nothing but 200 minus J 19.13, and the unit for the impedance is still ohm. So in this case, I will be EM over which is V over Z, which is 36.0 over 200 minus J 90.13. So it's still about the amplitude. So we take the absolute value of I, and then it will be 36.0, and then which will be 200 square plus 90.13 square, and then take the square roots. It will become 0.164 ampere. So this is the ampere of the amplitude of the phasor. And next, this should be B. So phi is arctangent. The imaginary part of Z over the real part of is it? No. Yes, 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 real part. So in this case, because we have the minus sign here, so phi will be something like this, and we just plug in this, and then it will become minus 90.13 over 200, and then take the arctangent. So this is minus 24.3 degree, or if you like radian, it will be minus 0.424 radian. You can pick either one. Okay. So something to talk about is for the phasor, V is not IR for the phasor. Actually, V equals I times Z. And Z is R plus J omega L minus 1 over omega C for series RLC. Okay. So next we talk about power in alternating AC circuit, power in alternating current circuits, which is AC circuit. The instantaneous way of the power dissipation in the resistor can be written like this: P equals I square R. I square R. This expression is always correct, no matter it is DC or AC source. But here in this case we have AC circuit, so I will be I square R times this term. So actually, we also define the average power dissipation because the power dissipation is time varying. It is a sine square x, sine square of this stuff, and actually you know that sine square x is nothing but 1/2 1 minus cosine 2x. Cosine 2x. So as long as cosine is a function between minus 1 and 1, so 1 minus cosine 2x is actually between 0 and 2. Because 1 minus, this one is between minus 1 and 1. So 1 minus 1 will be 2. 1 minus 1 will be 0. So this, so the denominator will be between 0 and 2, and if you just divide by 2, then this one is between 0 and 1. like this, I'm showing in this figure. So so actually we also need to concern about the average power, which can be calculating like this, we can just integrating this function for a single period, because it is a periodic function. So we only need to consider the average power within a period. Then it will be fine. And actually, for calculating this integration, we actually use this relationship. We have 1/2 1 minus cosine 2x, and actually the integration is from 0 to the period, and this integration is dy by t, so that this is the average value of this one. And as long as you know, these two are constant. These two I and R are constant, so that you can just break it out. So it doesn't really matter. We only care about how does these two come from. And so we calculate this integration, and we integrate the 1 and also the cosine 2x, and this one will be integrating 1 will be t, and then we substituting capital T and 0 and subtract them, so that we have t, and then this t and that t will be cancelled. So we have 1/2. And for this one, cosine, you integrate cosine 2x, you integrate by a period, then it will be 0. Because half of it is positive, half of it is negative. They can be perfectly cancelled. So final answer is 1/2. So it turns out that the average of this function is perfectly 1/2. It's perfectly 1/2. And actually you can simply consider, if you cut it like this, you can just move this part into here, and then you move this part into here, so that it is perfectly 1/2. You can just observe it from the figure. So we know that the P average is I square R over 2. And if we just put this 2 into the square, so that we have a square root of 2, I over square root of 2, and then take the square. So we will call this one a root mean square value of the I. I is the amplitude. And the root mean square of a sinusoidal is nothing but the amplitude divided by square root of 2. So we have a root mean square of the current is like this, and the root mean square voltage is also like this, because they are both sinusoidal. And after we consider the root mean square value, we can write it like this. So it will still look like this expression, but here, when we consider the average power, we use the root mean square value instead of the amplitude or whatever to calculate the average power. So generally, for RLC circuit, the average power is something like this. P average will be IRMS times the VRMS times the cosine phi. Phi is still this one. So it's still related to the impedance, because you can consider like this. As long as we have a Vt equals to Em cosine dt and It equals to Em over absolute value of C and cosine omega dt minus phi. So when we need to calculate the P average is 1 over t from 0 to t, and then Vt multiplied by I of t dt. So that within this integration, we have cosine times cosine like this. And actually, you know that cosine alpha minus beta is nothing but cosine omega dt cosine phi plus sine omega dt sine phi. So when you multiply this term by this one, you have cosine square, and cosine square, you integrate it, you will simply get 1/2, but you need to multiply by this cosine phi. So we have cosine phi here. And for the second term, you have cosine omega dt multiplied by sine omega dt, which will be 1/2 of sine 2x. And when we integrate, or I should write it as omega dt. And when you integrate this by a period, then it will be from t0 to t dt, then it will be 0. So that this one vanish, and then we will have 1/2 for this, and then we will have cosine phi like this. So that we can use the IRMS times the VRMS times the cosine phi for the P average. Okay. So we have a sample problem. Okay, so with a RLC circuit, ERMS is like this: FD, R, ZL, ZZ, and what are the power factor? Power factor cosine phi, and the phase constant phi of the circuit. Okay, so yeah, so actually still we use Z equals to R plus J omega L minus 1 over omega C, something like this. So R is 200, and we will have ZL is J 80.0, and then ZZ is minus 150. So Z is 200 minus J 70 ohm. So this is the impedance of this RLC circuit, and thus phi will be nothing but arctangent, the imaginary part of z, which is minus 70, and then divide by the real part of the z is 200. So phi is minus 19.3 degree. 19.3 degree. So in this case, cosine phi is cosine minus 19.3 degree, which is 0.944. So we have the phase constant and also the power factor. So they are, well, yeah, the power factor is cosine phi, which is dimensionless. So next, what is the P average? Dissipate in the resistor. Well, so we have Z. The absolute value of Z is 200 square plus minus 70 square. Take the square root, which is 211.9 ohm. So this is the absolute of Z, and P average will be E RMS square over Z cosine phi. Because ERMS is nothing but VRMS, and IRMS is nothing but ERMS over absolute of Z. So this one will be VRMS times IRMS, and then we multiply by cosine phi. So ERMS is 120 square over 211.9, and then cosine phi is 0.944. So P average will be 64.1 watt. And for part C, what is the capacity? The new capacitance is needed to maximize P average if the other parameter of the circuit are not changed. Which means that we hope to maximize the P average. In this case, we as long as the P average will be something like this, which means that if we want to maximize P average by changing the capacitance, we would like to maximize the phasor of the current, which means that we hope to make it like 1 over j omega c nu equals to minus ZL. And in this case, which will be minus J80 ohm. J80 ohm. So C new is J omega D, J omega D minus ZL. Oh, not this. No, not this way. It should be something like J omega D minus ZL, and then we take the inverse. So it will become something like 2 pi 60, and actually we have J, and then we have minus J80. So J times minus J will be 1, and then finally we will get C new is 33.2 mil farad. And in this case, the overall impedance of this RLC circuit will be a real number. So it will have the maximized P average.